Alright, before we begin on partial derivatives, we need to touch a little bit on multivariable equations, functions. Functions. A standard variable function is simple. Fx, let's say, equals to 4x2 plus 3x. Simple, right? So we put a 2, 4, 2, 2 plus 3 times 2. So this, let me put 3 through a calculator. Simple, 22. As for a multivariable function, it's fx and an extra y, or maybe more, maybe an extra z, g, etc., etc. For this example, we'll go with 9x3y plus 7y2. Sure. Now, if we put x as 3 and y as 5, like this, 9 times 3 to the power 3, since x is 3, and y being 5, it'll be 5. So 7 times 5, like this. Calculate it again. So we'll come up with a whopping 1,900. No, 1,390. Yes. So that's a simple explanation of the multivariable functions. And now, partial derivatives, probably. Let me get rid of this first. Partial derivatives. Alright. So a partial derivative, simple. Let's go with like equals fxy. And if we partial derivatives, there are first orders and so on and so forth. Depends on how much you want. The second and third, if the question even asks for it, is essentially you chain the x, yeah, like this. If it's a singular derivative, then it's just d z, since we put here z, dz dx. But if it's second, it could be dz dx, and then chain it up with dz and another dy. And third, you get it, so on and so forth. As for this fxy, if it wants the derivative to x, then you will derive it with x, only with the x, and derive this, and this y will be treated as a constant. Same goes with the other way around with y. X being constant, y being derivative. So an example being fxy, let me just put this up first. Fxy equals to 3x minus x2 y2 plus 2x to the power 3 times y. Now, for the fx, xy, we won't copy this, so we just look from over here. So, x, 3, 1, minus, since it's 2, so 2x. Right, the y remains unchanged since it is still part of the same, section of it, so it stays as a constant. Plus 3 times 2, 6x 2y, like this. Yeah, like this. But if it's in y, like this, xy, then it's, since 3x there is no y in it, it will be treated as a constant, and since it doesn't have y, it becomes a 0. As for this one, it's 2x2y. Yeah, though since the 2 becomes the, yeah. And for this one, it's simply 2x3. Alright, continue on with another example. And the second example, let's say fxy equals to x e exponential to the power of x to the power of 2 and the y. So let's go with fx xy. Then since this is a two-way, it will be needed to be done with the product rule. So it's technically x to y. So this will be 1. The x here is derived, and ignore, and this part is left as a normal one, times this thing. It is still an like this. So it's still x e x to y, and since it's derived with up here, so it will be 2xy. Putting that together, e x to y, since it's a 1, is integrated into it, times 2x to the power 2 y e x to the power 2 and y. And relating to this, real world applications. Real world applications. The aerodynamics, Navier-Stokes equations. Essentially, the Navier-Stokes equations, it helps to figure out the movements of viscous liquid substances. I wrote that wrong. Substances. So yes, viscous liquid substances. And it also helps to figure out how air flows. How air flows specifically around, let's say, planes. Yeah, just planes. This helps them figure out the best design and what type of material they should use to maximize airflow and aerodynamics. Yes. And another thing is Maxwell's relations. Now this one is related to a lot of thermodynamics. Essentially, the real application for partial derivatives is temperatures, pressures, heat capacity, chemical potential, and also used to describe how different thermodynamics variables relate. It also helps to build accurate equations in much more complex systems, like how gas behaves, how energy flows, and how a machine reacts to environmental changes. And yes, that's about it. So the important part is it helps figure out the more dynamic stuff. Because, well, since it's already mentioned in names, aerodynamics and thermodynamics. Temperature, pressures, heat capacity, chemical potential, the movement of viscous liquid substances using the Navier-Stokes equation also helps with airflow, and the lots of thermodynamics related stuff. Yes, right, thank you.